we mentioned above the reduction formulas for secant and tangent, and we can always convert an integral of a high power of secant and tangent eventually to something small, either the secant of x, secant squared of x, secant cubed of x, or tangent of x, tangent squared of x, and tangent cubed of x. And once you get to that point, then it's very important to know how to integrate that small power of secant or tangent, or if you're using reduction formulas for cosine and sine, being able to integrate small powers of cosine and sine. Let's start with the small powers of secant. The integral of secant of x is the natural log of the absolute value of secant of x plus tangent of x plus a constant. There's a little bit of a trick to this. If I want to integrate secant, what I can do is multiply by the quotient secant of x plus tangent of x over secant of x plus tangent of x. And then this function, this new function, is still equal to secant of x. Multiplying secant of x by the numerator there, I get secant squared of x plus secant of x times tangent of x, and the denominator is secant of x plus tangent of x. Now, if I let u equal secant of x plus tangent of x, we see that its derivative is the numerator. So we end up, after making that substitution, with the integral of 1 over u du. And its integral is simple. It's the natural log of the absolute value of u. And then we convert back to functions of x, and we get the natural log of the absolute value of secant of x plus tangent of x plus some constant. The integral of secant squared is very easy because we know the derivative of tangent is secant squared, so that's equal to tangent of x plus a constant. Let's have a look at secant cubed. How might I integrate that? Well, let's try the integration by parts and see if we can reduce it to the integral of either secant squared or secant. Let's let u equal secant of x and dv equal to secant squared of x. That's writing secant cubed as u times dv here. And of course we can integrate dv because its integral is just tangent, and we can find the derivative of u, that's secant of x times tangent of x dx. Now, at first glance, that looks a little more complicated than u, but everything is going to work out here. So we have the integral of secant cubed of x dx is the integral of secant squared times secant dx, which is u times v minus the integral of v du. So it's secant of x times tangent of x minus the integral of v, which is tangent of x, times du, which is tangent of x times secant of x. So that integral is the integral of tan squared x times secant of x. And now we're going to write that tangent squared as secant squared minus 1. So our original integral, the integral of secant cubed, is now secant of x times tangent of x minus the integral of secant squared minus 1 times secant, which is the integral of secant cubed of x minus secant of x. So now our integral, the integral of secant cubed, is secant of x times tangent of x minus the integral of secant cubed, which is what we're looking for, plus the integral of secant, which is 2 powers less than what we started with. Letting I equal secant cubed and solving using our algebra, we get the integral of secant cubed of x dx is secant of x times tangent of x over 2 plus 1/2 the integral of secant of x. And now we've already worked out the integral of secant of x. That's the natural log of the absolute value of secant of x plus tangent of x plus c. So we've completely solved for the integral of secant cubed, using this method of reduction to reduce the power in the integral by 2 and solving the integral for the lower power. For powers of secant which are larger than or equal to 3, we can apply the integration by parts to reduce the problem to integrating secant to the n minus 2. And of course, if we started with, say, the integral of secant to the 5, then our expression would involve the integral of secant cubed, and then we could apply the integration by parts again, as we had above, to reduce the power by 2 to the integral of secant, and the integral of secant we know how to do. What about powers of tangent? Well, let's start with tangent to the 1. That's the integral of sine over cosine. A simple substitution. U equals cosine will work. We get du equals minus sine of x dx. And when I substitute, I get the integral of minus 1 over u du, which gives me minus the natural log of the absolute value of u plus a constant, and the integral is minus the natural log of the absolute value of cosine of x, which is the natural log of the absolute value of 1 over cosine of x, which is the natural log of the absolute value of secant of x. The integral of tangent squared is the integral of secant squared minus 1. We know the integral of secant squared is equal to tangent, so this is tangent of x minus x plus a constant. What about tangent cubed? Well, I can break it up into tangent squared times tangent, which is secant squared minus 1 times tangent. And now I'm looking at the integral of secant squared of x times tangent of x minus the integral of tangent of x. Now I've already solved the integral of tangent of x, and for the integral of secant squared of x times tangent of x, I can just use u equals tangent of x, its derivative is secant squared of x, and I get u squared over 2. So the integral of tangent cubed of x dx is tangent squared of x over 2 minus the natural log of the absolute value of secant of x, or we can write that as plus the natural log of cosine of x plus some constant. For higher powers of tangent, we can derive a reduction formula again using integration by parts. It's a pretty simple reduction formula. The integral of tangent to the n is tangent to the n minus 1 of x over n minus 1 minus the integral of tangent to the n minus 2. So we can continue reducing the powers by 2 until we get to a power that's small enough to integrate.